One classified Pentagon slide stunned senior analysts. During a briefing in the spring of 2023, at least 3 officials reportedly leaned forward when the image appeared. It wasn't a missile, warship, stealth aircraft, or hypersonic weapon, the technologies that had dominated defense discussions for years. It was a transport vehicle built to move heavier loads faster and with greater precision than anything currently operated or publicly planned by the United States. As the slide remained on screen, one analyst reportedly whispered 3 words: "We missed this." The problem with moving things fast here is a truth about military and economic power that textbooks mention briefly and then move past, because it is unglamorous and difficult to photograph. Capability without mobility is just potential. It doesn't matter how advanced your weapon system is, how sophisticated your manufacturing base is, or how large your stockpile of critical materials happens to be. If you cannot move those things to where they need to be, faster than your adversary can respond, you do not have an advantage. You have an inventory. This is the lesson that every serious military strategist from Sun Tzu to Eisenhower understood intuitively, and it is the lesson that tends to get underweighted in public conversations about geopolitical competition, because transport vehicles are not as exciting as fighter jets. Nobody makes a movie about a logistics truck. Nobody writes breathless headlines about a cargo aircraft's payload capacity. And so, decade after decade, the unglamorous science of strategic mobility gets quietly underfunded, underreported, and underestimated, right up until the moment it becomes the decisive factor in a conflict or an economic competition. History has a way of making logistics look obvious in hindsight. It almost never looks obvious in the budget meeting. The United States learned this lesson painfully in the early stages of every major military operation it has conducted since the Second World War. Getting the firepower to the fight fast enough and in sufficient quantity is almost always harder than the planners expected. The logistics tail is almost always longer, more fragile, and more expensive than the combat capability it supports. The American military has spent decades and hundreds of billions of dollars trying to solve this problem, and it has made genuine progress. The C-17 Globemaster, the CH-47 Chinook, the Navy's fast combat support ships. These are serious pieces of hardware. They represent real engineering achievement and real strategic investment. China watched all of this. It studied the failures and the successes. It read the same after-action reports and the same strategic assessments. And then it went away and built something that the American defense establishment, which prides itself on anticipating what adversaries are developing, did not fully see coming. Not because China hit it perfectly, but because the assumption embedded deep in Western defense analysis was that China was still catching up, still a generation behind, still working through problems the United States had already solved in the 1980s and 90s. That assumption is now being revised urgently. What China actually built. Let's be precise about what we're talking about, because this story involves several distinct platforms that are often conflated in media coverage, and the conflation matters because each one represents a different dimension of the same strategic push. The platform drawing the most immediate attention is China's heavy tactical transport ecosystem, centered on the Jian Y-20, which entered People's Liberation Army Air Force service in 2016, and has been upgraded at a pace that Western analysts describe as aggressive. The Y-20 is China's answer to the C-17. It carries a maximum payload of 66 tons, has a range of approximately 7,800 kilometers, and can operate from shorter, rougher runways than its American counterpart. That last capability matters enormously. In the Pacific theater, the ability to operate from austere or damaged airstrips is not a nice to have. It is a survival requirement. But the Y-20 is almost the conventional part of this story. The part that made those analysts lean forward is what China has been developing alongside it, a family of ground-based heavy transport platforms using electromagnetic drive systems, advanced composite materials, and AI-assisted autonomous navigation that are, depending on who you ask, either a revolutionary logistics capability or the most consequential transport development since containerized shipping. And almost nobody outside a specialized circle of defense researchers has heard of them, which, now that I think about it, is probably exactly how China prefers it. The electromagnetic heavy freight systems being deployed across China's western military logistics corridors are not maglev trains in the conventional sense. They are modular, partially autonomous freight platforms operating on elevated guideways engineered specifically for high payload, high-frequency military and dual-use logistics. They carry loads that would destroy conventional road infrastructure. They operate at speeds that make long-haul trucking look like a different century. And they are being deployed at a scale and in locations that tell a very specific strategic story to anyone reading the map carefully. Then there is the cargo drone dimension. China's CASC, the China Aerospace Science and Technology Corporation, has developed heavy lift unmanned aerial cargo systems with payload capacities overlapping with manned transport helicopters. The CH series cargo drones, some with payload ratings approaching 2 tons, are not consumer products. They are purpose-built logistics platforms designed to move critical supplies across terrain that ground vehicles cannot traverse and in threat environments where manned aircraft are too expensive to risk. They have been tested extensively in Tibet, in the high-altitude terrain of Xinjiang, and in maritime scenarios in the South China Sea. And they work. The engineering behind the impossible here is where the story gets genuinely interesting, and where the gap between what China has achieved and what Western engineers expected becomes most apparent. The core engineering challenge in strategic heavy transport is a triangle of competing demands. You need payload, which means structural strength. You need range or speed, which means power efficiency. And you need operational flexibility, which means you cannot build something so specialized it only works under perfect conditions. Every transport system in history has made compromises somewhere on that triangle. The question is where and how much. China's approach involved a material science breakthrough that took roughly 15 years of parallel investment across multiple research institutions to achieve. The structural components of these platforms use carbon fiber reinforced polymer composites combined with high-strength aluminum lithium alloys in a layered architecture that delivers structural rigidity comparable to steel at roughly 40% of the weight. That weight reduction cascades through the entire system. A lighter platform needs less propulsive force. Less force means smaller power systems. Smaller power systems mean lower energy consumption per ton kilometer. Lower consumption means either longer range or higher payload for the same energy input. The engineering compound interest on a materials breakthrough of this magnitude is enormous. It doesn't just improve one thing, it improves everything downstream of it simultaneously. The propulsion systems use a linear induction motor architecture that China's research institutions have been refining since the early 2000s, initially for civilian high-speed rail applications. The technology that made Shanghai's Transrapid Maglev work in 2003 was not abandoned when that project stalled. It was studied, iterated, and redirected. 20 years of incremental improvement on linear electromagnetic propulsion, funded continuously through China's military civil fusion research framework, produced a system that can accelerate a 60-ton payload to operational speed using a fraction of the energy that diesel-powered heavy transport consumes per equivalent ton kilometer. The autonomous navigation layer is arguably where China's investment in artificial intelligence pays its most consequential dividend in this domain. These platforms are not remotely piloted in the way most people picture. They are not being driven from a control room by a human watching a video feed. They are running onboard AI navigation systems that fuse data from radar, LiDAR, multispectral cameras, and satellite positioning to build a real-time three-dimensional model of the operating environment and make continuous navigation decisions without human input. A human operator sets the origin, the destination, and the priority parameters. The platform handles everything in between, including obstacle avoidance, route optimization, and coordination with other platforms in the same logistics corridor. The terrain performance figures from testing in Tibet and Xinjiang are the numbers that stopped Western engineers mid-sentence. These platforms operate at altitudes above 4,500 meters above sea level, where diesel engines lose roughly 30% of their power output due to reduced air density, and where human operators experience cognitive impairment from hypoxia. The electromagnetic drive system loses nothing to altitude. The AI navigation system does not get altitude sickness. In high terrain, which is precisely the terrain that matters most in any potential Indo-Pacific conflict, these platforms outperform every diesel-powered alternative by a margin that is not incremental. It is categorical. The numbers that change the conversation. Let's talk about the data points that moved this from a technical curiosity to a line item in congressional briefings. The Y-20, in its current production variant, carries 66 tons over a combat radius covering the entire South China Sea and reaching deep into the first island chain from multiple basing options on the Chinese mainland. China's People's Liberation Army Air Force is currently operating somewhere between 50 and 80 of these aircraft, with production continuing at the Xi'an Aircraft Corporation at a rate Western analysts estimate between 12 and 18 aircraft per year. At that pace, the PLAF's Y-20 fleet will approach 200 airframes by the end of the decade. The United States operates 222 C-17s, and the United States is not currently producing anymore because the production line closed in 2015. Read that again slowly. China is building its strategic airlift fleet at scale. The United States stopped building its equivalent platform a decade ago. On the ground transport side, the electromagnetic heavy freight corridors operational or under active construction in China's western regions represent a logistics throughput that defense analysts estimate can sustain a force of several 100,000 personnel with all their equipment, ammunition, and supplies across terrain that previously made large-scale military logistics essentially impossible. The Tibetan Plateau, which shares a border with India and sits above the entire South Asian theater, was for decades a natural barrier to force projection. Not because China lacked the forces, but because supplying and sustaining them at that altitude was prohibitive. The electromagnetic freight systems being built there are not solving a commercial logistics problem. The commercial case for those routes barely exists. They are solving a strategic problem, and they are solving it comprehensively. The cargo drone numbers are perhaps the most startling in terms of pace. China has gone from 0 operational heavy lift cargo drone systems to a deployed fleet of several hundred platforms across military and dual-use applications in approximately 6 years. For context, the United States Army's Future Long-Range Assault Aircraft program has been in development for over a decade and has not yet reached operational deployment. The pace differential is not a rounding error. It is a structural difference in how quickly each country can move from engineering breakthrough to fielded capability. This didn't come from nowhere. This is the part of the story where the narrative of sudden Chinese technological emergence starts to fall apart, because what looks like a surprise is actually the product of decisions made 30 and 40 years ago that very few people in the West were paying attention to at the time. In 1978, when Deng Xiaoping launched the reform and opening up policy, one of the least discussed elements of that strategic pivot was the decision to treat infrastructure investment not as a consequence of economic development, but as a precondition for it. Build the roads, the rails, the ports, and the airports first. Then the economy will grow into them. Western economists at the time called it a misallocation of resources. Why build infrastructure for an economy that doesn't yet exist? The answer, 45 years later, is sitting in the Gobi Desert humming along an electromagnetic guideway at speeds that diesel trucks will never match. China's military-civil fusion policy formalized under Xi Jinping, but rooted in strategic thinking that goes back to the 1980s, created a research and development framework where civilian and military technological development are not separate pipelines drawing from separate budgets. They are the same pipeline. When Chinese high-speed rail engineers solved electromagnetic propulsion on difficult terrain, that solution flowed directly into military transport research programs. When Chinese materials scientists developed lightweight composite structures for commercial aerospace, those materials showed up in military logistics platforms within years, not decades. The result is a compounding effect that Western defense analysts refer to with barely concealed discomfort as dual-use acceleration. Every yuan invested in civilian technology infrastructure in China has a higher probability of generating military capability than the equivalent dollar invested in civilian technology in the United States, because the pipelines between the two domains are shorter, faster, and more deliberately managed. This is not an accident. It is a policy choice pursued consistently across multiple administrations. The research institutions that produced these breakthroughs are not obscure. The Harbin Institute of Technology, Northwestern Polytechnical University, the National University of Defense Technology. These are large, well-funded, internationally publishing universities whose work on materials science, electromagnetic systems, and autonomous navigation has been visible in open literature for years. The surprise is not that China built this. The surprise is that the signals were there all along, and Washington's conclusion was still that China was a generation behind. What the Pentagon is actually worried about. Let's be specific about the strategic concern, because the Pentagon is not worried about China's transport vehicles in the abstract. It is worried about them in a very particular operational context. The scenario driving American strategic planning in the Pacific is some version of a conflict over Taiwan that unfolds faster than the United States can respond. The entire logic of American deterrence rests on the assumption that the United States can get enough capability to the theater fast enough to either deter Chinese action or defeat it if deterrence fails. That assumption depends critically on logistics, on the ability to move aircraft, ships, munitions, fuel, and personnel from Hawaii, Guam, Japan, and the continental United States to positions close enough to matter before the conflict is decided. China's transport developments attack that assumption from multiple directions simultaneously. A Y-20 fleet approaching 200 airframes gives China the ability to move ground forces, equipment, and supplies across the theater at a pace that compresses the timeline of any potential operation. Compressed timelines mean less time for the United States to respond, position, and deploy. Less time to respond means the deterrence calculation changes, and it doesn't change in America's favor. The electromagnetic ground corridors in Western China change the calculus differently. They solve China's interior logistics problem. For decades, China's geographic size and the difficulty of moving forces quickly from the interior to the periphery was a limitation as much as an advantage. It took time to mass forces on a border. The electromagnetic freight infrastructure now operational or under construction in Tibet, Xinjiang, and along the northern border reduces that massing time dramatically and makes sustained operations in those theaters logistically feasible in a way they simply were not 10 years ago. The cargo drone dimension worries American planners for a slightly different reason. In a contested environment where air defense systems on both sides make conventional airlift dangerous or impossible, autonomous cargo drones offer a logistics capability that operates below the threshold of most air defense systems, at lower cost than manned aircraft and with no risk to human aircrew. The ability to sustain forward deployed forces with autonomous air logistics in a high threat environment is a capability the United States does not currently have at meaningful scale, and that China is actively fielding right now. The civilian dimension. Nobody is talking about here is the part of this story that almost never makes it into defense-focused coverage, and it is, in purely economic terms, probably the more consequential dimension of the two. The same electromagnetic heavy freight technology being deployed in military logistics corridors is simultaneously being used to solve a civilian logistics problem of staggering scale. China moves approximately 50 billion tons of freight per year. Let that number sit for a moment. 50 billion tons. The infrastructure required to move that volume efficiently determines the competitiveness of Chinese manufacturing, the cost of Chinese exports, and the economic integration of China's vast interior with its coastal industrial centers. Road freight in China is constrained by driver availability, fuel costs, road maintenance, and the physical limits of what heavy vehicles do to road surfaces over time. A 40-ton truck hammering a highway at 100 kilometers per hour destroys road surface at a rate exponentially higher than a passenger car doing the same speed. The maintenance costs are enormous, and as Chinese wages have risen and driver shortages have emerged, the cost advantage that cheap labor once provided has steadily eroded. The electromagnetic freight platforms address every one of these problems simultaneously. They run on electricity from China's growing renewable energy base. They are fully autonomous, eliminating the driver shortage entirely. They operate on dedicated guideways, removing them from shared road infrastructure. And they run 24 hours a day, 7 days a week, without shift changes, rest breaks, or the human error that makes nighttime trucking disproportionately dangerous. The economic geography implications are profound. China's interior provinces, historically disadvantaged by the cost and time of moving goods to port, are now connected to coastal logistics networks by high-speed freight infrastructure at a cost per ton kilometer that is transforming where companies choose to build factories. Locations in Chongqing, Chengdu, Zhengzhou, and Xi'an, served by high-capacity autonomous freight corridors, are now economically viable manufacturing bases in ways they were not a decade ago. China is not just building transport vehicles, it is reshaping its own economic geography in real time, and the productivity gains from that reshaping will show up in global manufacturing competitiveness in ways that Western economists are only beginning to model. The global reach question. Now zoom out, because this story doesn't end at China's borders. China's Belt and Road Initiative is fundamentally a logistics infrastructure project. It is building roads, railways, ports, and pipelines across Central Asia, South Asia, Southeast Asia, Africa, and Latin America, creating physical connectivity between China and markets and resource suppliers across the developing world. The public debate has focused heavily on debt diplomacy and whether recipient countries are trading infrastructure for sovereignty. These are legitimate concerns, but the less examined dimension is the operational one. What does Belt and Road look like when the transport platforms moving goods along those routes are Chinese electromagnetic freight systems operating at speeds and costs no competing logistics provider can match? What does it mean for Central Asian economic integration when autonomous Chinese freight platforms can move goods from Xinjiang to the Iranian border in a fraction of the time and cost of conventional rail or road freight? What does it mean for African development when Chinese cargo drone systems can deliver to locations that have no viable road or rail infrastructure at all? The answer that makes governments and strategists uncomfortable is this. The transport infrastructure advantage compounds the trade and investment advantage. If you build the road, you shape the traffic on it. If you build the logistics system, you shape the supply chains that depend on it. And if your logistics system is categorically faster, cheaper, and more capable than any alternative in that market, the economic relationships that form around it tend to be durable. Switching costs are high, alternatives are slow. Dependencies, once formed, are difficult to unwind. Several countries hosting Belt and Road projects are already in conversations with Chinese companies about deploying next-generation autonomous freight platforms on those same corridors. The deployments are not yet at scale. But the trajectory is clear enough that the United States, which has its own infrastructure diplomacy initiatives in the developing world, is paying attention to the logistics technology dimension of China's global reach in a way it simply was not 5 years ago. Where this goes next here is the conclusion that serious analysts on both sides of the Pacific are converging on, though they express it with varying degrees of alarm depending on their institutional affiliation and their tolerance for being quoted publicly. China's transport vehicle development is not a program with a finish line. It is a direction. And the direction is toward a logistics capability that is faster, more autonomous, more capable in difficult terrain, and more economically efficient than anything currently operating or on America's near-term development roadmap. Every year that direction continues, the gap does not stay the same. It widens. The Y-20 production line is running. The electromagnetic freight corridors are being extended. The cargo drone fleet is expanding. The research institutions that produced the current generation of platforms are already working on the next one. And the military-civil fusion pipeline ensures that every advance in Chinese autonomous vehicle technology, every improvement in battery and power systems, every breakthrough in composite materials has a shorter path to operational military logistics capability than its equivalent in the United States. The window for the rest of the world to respond is not closed, but it is narrowing, and the first step toward closing the gap is acknowledging that it exists, which requires setting aside the assumption, still surprisingly common in certain quarters of the American defense establishment, that Chinese logistics technology is fundamentally derivative and fundamentally a step behind. It is not a step behind. In specific domains that matter enormously to strategic competition in the Pacific and to economic competition globally, it has moved ahead. The analysts who leaned forward in that briefing room understood this the moment that slide appeared. The question now is whether the institutions they work for can respond with the urgency the situation actually demands. Because in the Gobi Desert and in Tibet and along the logistics corridors of the Belt and Road, the machines are already running. They don't need anyone to believe in them. They are simply doing what they were built to do, moving things faster, farther, and more efficiently than anything that came before them, and doing it in a silence that the rest of the world is only now beginning to hear.